This year's prize is about light. The Royal Swedish Academy of Sciences has decided to award the 2014 Nobel Prize in Physics to Professor Isamu Akasaki at Meiji University, Nagoya, and Nagoya University, Japan, Professor Hiroshi Amano at Nagoya University, Japan, and Professor Juji Nakamura at University of California, Santa Barbara, USA, for the invention of efficient blue light emitting diodes, which has enabled bright and energy-saving white light sources. Professor Delsing will now give us a short summary in English, please.
So today the Royal Swedish Academy of Sciences is awarding the Nobel Prize in Physics for the invention of blue light emitting diodes. Red and green LEDs have been around for many years, but the blue was really missing. This lamp contains 3 LEDs, one red, one green, and one blue. If you combine these colors, you get white light. This is something that Isaac Newton showed already in 1671. Thanks to the blue LED, we can now get white light sources which have very high energy efficiency and very long lifetime. This LED technology is now replacing older technologies. In fact, many of you carry this technology in your pocket. The flashlight and also the screen of modern smartphones uses LED technology. Professor Olle Inganäs will now continue and give you some of the details.
And we will continue to look at the history of lighting, which has been around now for the last few millennia of human evolution. We started out by burning fuels inside lamps. In the geometry, quite similar to that lamp we see over there. However, that has mainly been used here at KVA using incandescent lighting and electrical light. Over the last 100 years or so, since Edison invented these things, the fluorescent lamp was introduced somewhere in the early 20th century. And then we saw much later the arrival of the lighting element that we are now celebrating in this year's Nobel Prize. And what you see is, of course, an enormous increase of the power efficiency, of the use of electrical energy in generating light. Now, something like 1/4 of our electricity consumption in most industrialized economies goes to illumination. So these effects, having much more light for much less electricity, is really going to have a big impact on our modern civilization. We see that impact. You see it in the streets, you see it on the cars, you see it in the lights, you see it in new optical environments like this one from a festival of lights somewhere in Japan. And they're all based on the use of these light-emitting diodes. They come in different colors, not only white, but blue, red, and green, as we saw here. And they have not only the advantage of much better using the electrical energy, they also give a very much longer lifetime, maybe 100 times longer than that of the standard incandescent lamp that is now being going in retirement. Also, it doesn't bring the mercury along that the intermediate generation of fluorescent tubes is contributing as a problem to industrial civilization. So we will most certainly be able to use this technology. But it took a long while to arrive at this possibility. The red LEDs have been around since the early 1960s. The green LEDs, some years later. Advances in semiconductor technology using band gap semiconductors with different band gaps lies at the base of this. But the blue thing, the blue light emitting diode, was very, very difficult to accomplish. Not that there was a lack of effort. There was continuous efforts in industries to generate blue light emitting diodes. Because today, with the advantage of having these available, we can generate all those colors. We can combine in color mixing with 3 different colors in the individual lamp, or we can use, as you find mostly maybe on the market today, a blue or UV emitting LED illuminating a thin layer, absorbing this energy and converting it to other colors. The structure of these lamps are very similar to what you have at the base of your semiconductor electronics that's driving the information technology. A diode, a combination of semiconductor materials where you have one layer carrying holes, one layer carrying electrons. They transport these charges at 2 different energy levels, but when they meet in this intermediate layer, the active layer, they recombine. And when they fall into each other, they turn up and turn light on. That was light. That was there. So this is the physical mechanism that lies at the heart of this device. And our laureates of this year have contributed greatly by the inventions that made it possible to grow the gallium nitride and alloys of gallium nitride materials in the particular geometry suitable for building such diodes. You have to be able to grow these, and that was attempted for 3 decades before the inventions of Akasaki, Amano, and Nakamura. You have to be able to form these diodes, and there was a great problem with passivation of the dopants being used to create these. It was solved by discoveries and inventions in these Japanese labs. And you have to introduce more colors, and you have to build them into structures which well confine the electrons and the hole searching each other in order to generate light emission. And these are the structures as you find it today, a great number of abbreviations on top of each other. Each layer may be a fraction of a micrometer thin, deposited from the vapor phase in big synthesis machines. What you see at the market might be a light bulb like this, where the tiny, tiny speck of matter with this structure, sub-millimeter size, is emitting quite a bit of light. Today, or yesterday, when this figure was compiled by satellite photographers of NASA, this is where we see light being generated in the industrial economies, mainly, and with the great urban areas of the world. But of course, the access to electricity is very weak in many areas of the globe. There is no electricity net. They don't have the electrical power generation accessible. This is changing because solar lanterns being used to generate light with little electricity help out in balancing the systems where you have solar photovoltaic plants and store them in batteries for use at night. So in the future, I believe this map will look different. And this is very much in the mind of Alfred Nobel, who wanted to give his prize to the inventions for the better benefit of mankind. And this is why we award this year's prize to Akasaki, Amano, and Nakamura.
Thank you, Professor Inganäs. And we are now trying to see if we can get Professor Nakamura on the phone. I should say it's about 3 o'clock in the morning, and I think I woke Professor Nakamura up just 15 minutes ago. So I say, good morning, Professor Nakamura. Are you there?
Yeah, good morning. I'm here. Yeah.
And congratulations. I'm sitting here in the session hall at the Royal Swedish Academy of Sciences, and we have a press conference with many interested journalists from Swedish and international press. And are you ready to take some questions from them, Professor Nakamura?
Yes, I'm ready.
Okay.
I'm almost sleeping. Yes, it's okay. Yeah.
Do we have any questions for Professor Nakamura?
Good morning, Professor. Congratulations. Omedetou gozaimasu. We have already heard, We have already heard some things said about the significance of your discoveries. Could you please, in your words, tell us about what you think is the significance of your discoveries?
Oh, my work is, I think the technique I clarified why we couldn't experiment, right? There is current. Also, other big breakthroughs in my case is the fast high-priced variety. Also, I developed a fast bioreactor diode. This is 3590.
It was very difficult to hear you. Your voice is breaking up here. Thank you.
Do we have some other questions?
Yes, congratulations. How did you feel being woken up like this in the middle of the night with the message that you have won the Nobel Prize?
Hello?
Hello?
Hello? Yeah, did you repeat the question again? No, yeah.
I don't know if you heard the question was just how what did it feel like to be waking up in the middle of the night with the message of that you'd received the Nobel Prize?
Oh yeah, it's unbelievable because I was sleeping. So, oh yeah, it's like yeah, amazing, unbelievable. Yeah.
Okay. Well. Thank you, Professor Nakamura, and from all of us here, we congratulate you once again, and perhaps you can sleep. Perhaps you can go sleep a few hours, but then I think there will be a lot of media outside your house. So thanks again.
Okay, thanks so much.
So, are there now any questions to our experts here at the panel? Something that you would like to have clarified? Please.
Yeah, my name is Sophie Chen Axelsson from freelancer for China Radio. I heard this prize is about the energy in LED. So when you consider this prize, do you consider the element that will be contribute to the society in practice more than in theory?
My response would be that we are cherishing the tradition that Alfred Nobel, who was a great inventor, he wanted his prize to be given to inventions for the benefits of mankind, and that's what we emphasize today, is the usefulness of this thing and the usefulness in so many applications. We emphasize very strongly the fact that it can be used for white lighting. But we've seen over the years how these inventions of the blue light-emitting diode was used in the blue laser diodes used for optical storage, how coming generations of communication will rely on the use of light rather than radio waves, in Li-Fi rather than Wi-Fi, and how you can use these blue or UV light in order to sterilize water. There are so many uses of this, and the uses, I think, is what would make Alfred Nobel very happy.
Something to add? Or? No.
No, I can add that this is really an invention prize. It's not maybe less a discovery prize as other prize, but invention prize. And in this type of prize, we really emphasize the usefulness of the invention, and this is the case in this case.
Do we have some more questions? If not, I'd like to. We have a question over there.
Yes.
Hello, I'm Oliver G. from the local Sweden's News in English. It was a little hard to understand Mr. Nakamura on the phone, but perhaps you could recount how it was to ring up and let him know that he'd won the prize, and we could hear it from your side.
Yeah, from my side, we reached 2 of the 3 laureates. Professor Amano happened to be on a plane from Japan to France at this very moment, so we couldn't reach him. But we could reach Professor Akasaki and Professor Nakamura. And of course, they are thrilled of getting this prize. And I think actually they were not prepared for it. They had not been waiting all day and all night for this call. And if you happen to be on a plane, I think that's how it is. And of course, it's a fantastic experience for us to be the first to wake them up or call them in the evening and congratulate them achieving the Nobel Prize in Physics. So that's a great honor on our part. Okay, if there are no other questions, I'd like to end this press conference and see you tomorrow when we are announcing the chemistry prize at the same time and in the same hall. Thank you very much.